Yes, so Cheng, did you say we start?
Good evening, Malim. You can start.
It's okay, thank you. Welcome back. We want to today look at methods of some algorithms for uh, factorizing composite numbers. If you're given a composite number, we learn how to factorize. And you understand that is the trick that RSA uses, that you multiply two prime numbers, bigger prime numbers, knowing that nobody can factorize to get back the prime numbers. But it was then discovered there are so many ways of factorizing those prime numbers. And so that is what we shall be looking at today. So I began by noting that the problem of factoring huge integers is very significant in cryptography. And the reason is that some cryptographic methods, such as RSA, use the difficulty in factoring numbers as their security. So they know that it's easier to multiply two prime numbers together, but then it becomes very difficult to factorize them back to the prime numbers. So that is what they do. For instance, when they talk of the public key and the secret key, the public key is known to everyone, and it includes a number n, which is a product of two numbers. And these two numbers are kept secret. But this one is released to the public. So they know that you can never get these two because they have it public. They have it private. They know it's impossible for anybody to factor this. And of course, it's almost impossible if they are very huge, if these two are very huge. But there are algorithms that can do that, can break this n, and give you these two. Once you have these two, you can get phi of m. You can get phi of m, and once you have phi of m, remember E was public, is a public key. You can get its inverse. And once you have the inverse, which is we call it D, when we are doing RSA, once you have this inverse, you can now decrypt that communication and get the initial message. Now, so that is what we'll be doing. So as I said yesterday, we'll try to see how to factorize composite numbers. And then when we meet on Thursday, we try now to do it. We have a few people coming up with the secret and the public keys, and then sending some numbers to each other. Then we try and decrypt without them telling us what their P and N P and QR. So we try and crack. Now, so the algorithms we'll be looking at, but today I'll just look at the first one, the Pollard's row algorithm. We have several algorithms. In fact, we have the very modern algorithm, which is the quantum. We have quantum algorithms, and one of them is the Shor's algorithm. These ones are very fast, and they can factorize a very huge prime number. They can factorize a very huge prime. So we shall look at all these algorithms slowly by slowly. And then as we look at them, you also try and write in your program so that when we meet, it becomes easier. We can now attempt to factorize very huge prime numbers. But in our examples, I just be showing smaller, not prime numbers, but composite numbers. In our examples, we shall just show very small composite numbers for working. So because the ones we can use our calculator to factorize. Now, so what is Pollard's row method? And what does it entail? So we need to know what it entails, and then from there I'll go straight to examples and show you how to use it to factorize. Now, so this algorithm, which we call the Pollard factorization algorithm, is based on what we already know, the congruence, the knowledge of congruence. And so you have some set value. We shall see how to come up with the initial value. And then you use that initial value with the other initial conditions. The initial conditions that you set. And then you use the knowledge of congruence to try and factor this number, n. So supposing that the number is n, we can factor it back to the prime factors. Remember that we're only factoring a composite number. So these algorithms only will tell us, will factorize the composite numbers. They're not algorithms to tell us, these are not the type of algorithms we use to tell if a number is prime. But we shall again look at other algorithms later that will tell us that this number is prime, you cannot factor it. Because it could be given a big prime number and you struggle with it to factorize, and yet it's prime. So we'll also look at algorithms that can tell us if a number is prime or not. Now, so I've said that this method will be using the knowledge of congruence. That's why I'm teaching it at this time, because we are now very much familiar with the congruence and how to handle anything to do with congruence. This method is very important for factoring medium, large integers. Yeah, what I mean by this is that if you give it a very huge composite number, it may not factorize, or it will take long to factorize. But as we shall see again, it's a very fast method compared to the other method where you try the trial, the one we use, we call trial method, where you're trying. You see, for instance, if you're given a number like, let me say, 27, and you want to know which are the factors of this number, what some people would do is you try 2, if 2 can divide, then you try 3, and so on until you find a number that can divide it. This method of trying is very long, especially if you're given a very huge number. And we shall see. The numbers we will be doing today are not very small, they're huge. And if you are to do it using trial, it will take a long time. So this method will it will be very fast factoring such numbers. But again, remember that it cannot be a very huge number. Remember, RSA is using very huge numbers. So this method, if you try to use, if anybody, that is why I said, if somebody uses smaller numbers, prime numbers, then they can easily be factored. We have so many methods, and this is one of them, and we shall see how small numbers will be factored. Now, so we just want to, we are given n and we want to just get one factor. Once you get one factor, we'll just be obtaining one factor. Once you get one factor, you know that you can get the other factor by just dividing. Just dividing. If you divide, you have the other factor. So that's what we'll be doing. We'll just be looking for one factor, and then you can divide and get the other factor. If there are only two factors, you are done. If there are several factors, you again proceed and get them. Now, so this is now what we'll be doing. I said that this method uses the knowledge of congruence. And before using the knowledge of congruence, you have some conditions that you lay, the starting conditions. So I want to begin by assuming that I want to factorize this number n. So if I want to factorize this number n, then I'll choose another number, x, randomly. I'll just choose an x, a random number, and then choose a constant, again, just random. And then I use this equation. I use this equation. So you know the x will be here. You just substitute x here, and then the constant here, and use this equation to factorize. Mod, you remember that this will then be mod n. We are doing it mod n. That's why we say we are using the knowledge of congruence. So we'll be doing this mod n. So this C, the C here is just any constant. Can be 1, can be 3, can be 5, can be 7. For me, I like using the prime numbers for C, but again, just an integer will just work. An integer will work. The initial x, so I'm saying you are choosing an x. You're choosing an x, and when you choose an x, the initial x, you also choose a y. The initial y and the initial x will be equal, but then they'll be varying as we proceed. They'll be varying as we proceed. Y will be moving faster than x. Y will be increasing faster than x. But at some point, they are likely to meet. X is likely to catch up with y, because we are using the knowledge of congruence. And so you see that although y will be moving like 2 steps faster, 2 steps ahead of x, but at some point is likely to catch up with y. And then we find the GCD. Now, so what we are doing, therefore, we go from x, and the initial x just want to cut. And this statement says, set the initial value of y equal to the initial value of x. So if my initial value of x is x naught, I'll say this x naught will be equal to my initial value of y, which I'll also call y naught. So I let my x naught be 2. And in most cases, when you're using this algorithm, your initial value of x is 2. Your initial value of x is 2. But what I said, we can always vary, if as you want, is the value of c. The value of c, you can vary it. but let the initial value of x be 2. Now, so these are the equations we will be using. So this is what we'll be doing, therefore. This is what we'll be doing. Let me just break down the whole mathematics and show you what we'll be doing. So what we do, we get x1, then get y1, get x2, then get y2, get x3, and then y3 as we proceed. Every time you get x1 and x and y1, find the GCD. Find the GCD. And what GCD are we finding? We are finding the GCD of, just create some space here so that you can see what we are doing. Let me just create some space here. So we have our x naught. We have our x naught and we have our y naught. Those ones are our initial values. So now from these initial values and using this equation, we find x1 and then find y1. When you find x1 and y1, the next thing you're supposed to do, find the GCD of y1 minus x1 together with the n. So what I'm saying is, you have the value of y1 and you have the value of x1. Subtract these two values and get the absolute value. What I'm saying, what I mean by that is that sometimes you can find that y1 is smaller and x1 is bigger. Subtract and get the positive value. Just subtract and get 2. Then once you get this 2, take the GCD of 2 together with the n, that GCD. In most cases, this GCD will be 1. In most cases, this GCD will be 1. If you find that GCD is 1, proceed and find x2, and then find y2. Once you find x2 and y2, find the GCD again of y2 minus y1. No. y2 minus x2. y2 minus x2 with the n. If you find this GCD is 1, proceed and find x3 and y3. Once you find this, find the GCD of y3 minus x3 with the n until you find a value that is not 1. When you find a value that is not 1, let's say you find k or n, let me say you find b. If you find a value that is not 1, you stop. You stop at that because you've already found a factor of n. You've already obtained a factor of n. This b will be a factor of n. So you can now divide n by b to get another factor. Now, sometimes you would find, okay, I've already explained what we are going to do. How are you getting x1 and x2 and x3? We are just using this equation. We have said that let x2 be, no, x naught be 2, for instance, and let our c be 3. So how do we get x1? To get x1, we just put the value of x naught here. Put the value of x naught where there is x. When you put the value of x naught is 2. When you put here 2 square, what you get is 4. 4 plus that is 7. That is 7 is our x1. So I'll be showing you again how to get y1 as we look at the examples. But the thing is, find x1, then find y1. y1, then subtract x1 from y1, find the GCD of that with the n. Can you hear me?
Yes.
Yes.
Yes, so let's proceed and let me just show you the algorithm so that you can also write an algorithm. Just showing you something that I think you can improve on it and write in Rust so that we can use it as an algorithm. I've said that, let me just read what I've been saying. I've said, and I've written it here, it's in words here. I've said we get x1 by substituting x naught in that equation, mod n. And then we also get y1. How do you get y1? We get y1 by, you see the equation that we have is this. This is the equation that we have. We have the equation f of x is x squared plus 1. Now let's assume that this is y. Let's assume that f is y. So if I assume that f is y, then it means y is this. This is our y, the first y. Now, supposing I want to get the second y, what I'm supposed to do is to substitute this equation inside here. Substitute, so that means I just put y, where there is x, I put y. Where there is x, I put y. And so where there is x, I put y. This is my y, x squared plus 1. Where there is x here, I put y. This is my y. But now I square. There's this square. I've just substituted x by the y. Then I square. Then I add 1. This is how we'll be getting the values of y. And that is what this says. This one is saying. What this one is saying is that I take my y naught, substitute it in this equation, substituting my y naught in this equation. After substituting it in this equation, the answer that I get, I again substitute it in this equation. And that's what I've just said in simple terms. That's what I've done in what I've done there. So let me just go straight to the example. Let me go straight to the example. And again, I'll rewrite these formulas. Now, let me just repeat what I've said. What I've said is, we want to use this algorithm. And what we do, we set our initial values. And our initial values we've said, let the initial values x naught be 2. And our y naught will also be 2. The initial ones will be the same. Y naught and x naught. So you are putting these two at the starting point. All of them, you put them at start line. But now you make y to be moving faster than x. And I've said, once you set these initial values, also set your equation. Also set your equation. And any equation, so long as it's x squared plus a constant. And in my examples, the constant I've used in my examples is 3. That's the constant I've used. And I've said you can use 1, you can use any constant there. Once you set these initial values, find x1 and find y1. Then subtract x1 from y1 and find the GCD. This is the algorithm. You can try to improve this and put in Rust what I've said. 1 to factor n. So we set our initial condition, x, let it be 2, and y, and this is the equation. This is the equation. This equation of you can even, yeah, it's okay the way it is. But what have I said? What I've said is, you then get x1, and I've used k, because when you're writing a program, you see you summarize. So I'm just saying, once you find x1 and get y1, you'll subtract y1 minus x1 and find that GCD combined with n. So in short, I have said, instead of you saying 1, and then there's x2 also and y2, and again find the GCD of y2 minus x2 with n. Instead of writing all of this, I've said the 1s, 2s, and 3s, I call them k. So what I've said, therefore, is that at every stage, you'll find the GCD of xk minus yk, whichever, so long as you get the positive number. It's either yk minus xk or xk minus yk, then with the n at every stage. This is what I said. If you find that the GCD is 1, you proceed and get the next x2 or y2, proceed and get x3 and y3, and get the GCD at every stage. If the GCD is 1, you proceed. If the GCD is 1, you proceed until you find a GCD that is not 1. The other thing is, if you find that the GCD is a number greater than 1, but less than n, you stop. You stop, because this GCD then represents that factor we are looking for. In some cases, you'll find that the GCD is n. These cases are rare, but then it says that if that happens, then it means the algorithm has failed. So you begin afresh. You'll have failed and therefore you begin afresh. But those cases are rare, where you'll find that the GCD will be the same, it will be n. Because n is the number 1 to factor. Let me go straight to the examples. The number 1 to factor is this. I set my initial x naught to be 2, and this is my, I said in these examples, I'll be using this as my, this polynomial. But I said again, 3 can be replaced by any number. Now I want to show you now how to do this algorithm. Our x naught is 2, and we said that initially y naught will also be 2. So what we'll be doing, therefore, is that we have this equation, x naught on x squared plus 3. So when k is 1, I want to get my x1. When k is 1, that's what I mean. When you say this is my xk and yk. So when k is 1, so what is my x1? What is my x1? My x1, I take my naught, x naught, which is 2. So my x1 would be 2 squared plus 3, which is what? 7. What about my y? I had given you a formula already for getting y. I had said that for us to get y, and let me write this formula just aside here, so that we will be referring to it. Y is given by x squared plus 3. So if this is so if I want to get f of y, So this, let me call this y naught, for instance. So if I want to get yk, what will I be doing? If I want to get yk, what I'll be doing, I'll be taking the value of y, taking the value of y just above. I take the value of y, for instance, the value that I want to get y1. So I take the value of y naught. I take the value of y naught and square it. After squaring it, just a minute, let me just write the formula. Just first of all, so what I said, the formula is, let me substitute this y here, that equation. The equation that I have is f of x is x squared plus 3. X squared plus 3. So I put y here. I put y there where there is x. So I have f of y as, where there is x, I put y. This is our y. This is our y. So this will be x squared plus 3, but then there's this square, then plus 3. Let me just change and write them. Instead of x, let me just change and write it as y, because that's what we'll be doing. So you take the y just above, the y just above, square it, then add 3, square the result, then add 3 to that result. And you are doing it mod n. You are doing it mod n. Now, so this is our table. We are finding the value of x1. So to get x1, we use x just above. X just above is x naught. And we also have y naught. X naught is 2. Y naught is 2. So what are we interested in is x1, x2, x3. These ones we are not interested in. These are just initial values. We are using them to get this. So for me to get y1, according to this formula, I take my y just above, which is 2, our x naught. Then square it. Then add 3 to that result. Then square the result. Then add 3. Then do it mod 2021. So that if it's bigger than 2021, we reduce it. So what do I get here? This will be 4 plus this. That is 7. When you square 7, you get 49. 49 plus 3, you have 52 mod 2021. So this one is smaller, you leave it. That 52 is there. So we found x1 and y1. So after finding x1 and y1, subtract x1 from y1. You get 45. When you subtract 7 from 52, you get 45. Then find the GCD of 45 and the 2021, our n, using the Euclid's algorithm. When you do that, you get 1. That is GCD is 1. If you find that GCD is 1, it means you proceed and find x2. So how do you find x2? We're using the x just above. So you take now, I want to get x2, this line. I take the x above, replace it in the equation. Replace it in this equation. Oh, the equation of x is here. Let me just write it. The equation that we are using for x, let me just make it clear here. We're using this to get x. So our xk is the equation we'll be using to find xk. And we have said the one we'll be using to find our y value is this one. So let me say that this is the equation that we'll be using to find our yk. Now let's now proceed and find x2. We take the x just above, which is 7, above 2, which is 7, and put it here in this equation. So 7 squared will be 49, plus 2 plus 3. So that gives us our x2 as 52. Our x2 is 52. Now I'll do several examples. I just want you to see what we are doing here. Now let's get our y2. Let's get our y2. We use the y above. This is the equation for yk. So to get y2, we take the y which is above, that is 52, put it here, square it, 52 square it, then plus 3, then square the result, then add 3 to that result, mod 2021. Let's just do that. Let's take using a calculator. Just opening my calculator. 52 square. Let's use our calculator. 52 square is I'm getting 2704. Then add 3. When you add 3, what do you get? When you add 3, you're getting 7 here. So this would be 2704, no, 07. Square this square here. Square that. Let's just square that. When I square that, I'm getting a very big value. Let me add 3 to it. Because there's this 3. Let me add 3 to that result. So what I have is 7327852 mod 2021. So that means I should divide by 2021 and note the remainder. Divide by 2021. It goes there 3,625 times. 3,000, it goes there 3,000. Let me just note it here. 3,625 times. Let me find the remainder. So the remainder now is, it went there 3,625 times. The remainder is 1727. 1727. That's the number you see here. That's the number you see here. After that, take this x2, subtract from y2. When you subtract x2 from y2, you get 1675. Find this GCD using the Euclidean algorithm. You'll find 1. When you find 1, it means you continue. You find x3. Let's find x3. X3 and y3. So we found x2, y2, and our GCD was 1 at the end. So that means we proceed. Now, Want to find x2? Our formula for xk still remains. Xk still remains is x squared plus 3. So if we want to find x3, that means we are using the x just above, which is 52. So x3 therefore becomes 52 square plus 3 mod 2021. You can see how important the knowledge of mod and modular arithmetic is very important. 52 square, I'm using my calculator. 52 square is 2704. And when I add 3, I have 07. I'm doing it mod 2021. So what is the answer? Let me see. So that means I divide by 2021 and not the remainder. 2021 goes there one time, once. The remainder is 686. That is my x3. 686. Let me get my y3. My formula is for yk is here. My formula for yk is here. Y just above is this one. This is the one I'm substituting there. So I square it. So it means I take 1727 squared, add 3, square the result, then add 3, and reduce it mod 2021. Just do that. Sometimes you'll discover that this one is very huge when you raise it to 2. So just reduce it first. Reduce it first, then add 3 to it. Still the same thing. What you're interested in is the remainder. So I can work out this one first, reduce it, then add 3 to it, then square the result. Let me just do that. 1727 squared is 2,982,529. That's a very huge number. Let me reduce it mod 2021. So let me divide by 2021. Because there are 1475 times, 1475 times 1475 times. The remainder is 1554. I add 3 to it and then square. Then add 3 to the result. Then reduce mod 2021. Now, so 1554 is what I remained with. When I add 3 to it, I get 1557. Square that. 1557, square that. I get 2,424,249. Add 3 to that result. When I add 3 to that result, I get 252. Yes. Divided by 2021, which goes there 1,199 times. What is the remainder? The remainder is 1073. 1073. Now subtract x3 from y3. You get 387. Find this GCD. When you do it, you find 43. 43 is not 1. So it means this 43 is a factor, of n. It means this 43 is a factor of n. That's what we began. Where we began, we said when you get GCD that is not 1, so long as it's between 1 and n, then that GCD becomes the factor. Let us see whether it's true. Let us see whether 43 divides 2021. 2021. Let's divide 43. Let's see whether it divides. 2021 divided by 43. Yeah, it goes there. Find that 43 goes there 47 times. Goes there 47 times. What I'm sure of is that this 43 is a prime number. I don't know about this. If it's a big number, you need to test whether it's a prime number. But what we are doing here, the GCD here will be a prime number, so this number will be prime. But this one sometimes may not. For this case, it could be prime, but sometimes it may not be prime. So it means, again, if you need to get all the factors, if this second number is not prime, it means you would proceed again to find its factors. Supposing you required all the factors, and supposing that this number is not prime, you would proceed again to find the factors of this other number. Now, that's a different question. You've done the first question was just to factor this. You factored that. So after that, you come up with another question, now factor this, and find all the factors of the original number. Now, so I know that that was the first example. You may not have grasped the concept. I will want again, but now you have a rough idea of what you are doing. I want us to proceed the second example and use the same steps so that you understand. Of course, these steps we'll be using them on Thursday in our practical lesson. Now, what you discover is that if you're using an algorithm, this algorithm makes your work easier. You can see it has made our work easier. How many steps do we have? We just have 3 steps. And you've already factored this number, 2021. But if you're using trial and error, you would have used several steps. You would have used several steps to do that. In fact, you may, because you're trying 2 refuses, you try 3, it doesn't, you try 4, and you see you are to try up to 43. You're trying all the prime numbers, you try up to 43. So for you to get the first number that will divide this number. Because when you are using trial, you are trying to check if this prime number can divide it. So you try 2. 2 is the first prime number you will try. It fails to divide 2021. You try 3 is the next prime number. It fails. You try 5 is the next prime number. It fails. You try 7. It fails. You try 11. It fails. You try 13. And you're doing that until the time you try 43, and then 43 accepts to divide the number. So you can see that method of trial, you used a lot of time. But this one, just 3 steps. And if you have an algorithm, then it's just a second. Just a second and you have the factors. But again, if you have an algorithm and you're using this trial, the algorithm will take long. If you make a program, and that is trial, you get the same result. You have told your program to try it will take long to try all of them. Let's look at this example. We set our initial x, we said it should be 2, and the y naught will also be 2. Initially, they begin at the same point, but y will be moving faster. Y will be moving faster than x, but they'll come at a point where they now be getting closer and closer because they're using this modular arithmetic. So they'll be getting closer again. And then we set our equation. And this constant can be any number. That's what he's saying. Now, what are our formulas? Our formula is the one, this is our formula. So our x, no, our xk will just be the value of x above squared plus 3. What about our yk? Our yk is the value of y above squared plus 3. Then you square this. Then add 3 to the result. And every time we are doing this, we are doing it mod 2029. We are doing it mod 2029. These are our formulas. So we just now use them. Find the values. For you see, supposing you had multiplied your two prime numbers and they're this small, and n is public key, everyone knows it, and e is also known. You see, if we get this, you can decrypt this. You can decrypt the message that you have. Just use this method, and there are several other methods. Now, so what is our x1? Our x just above is x naught. X naught is 2, put it here. So it's 2 square plus 3, which is 7. So our x1 is 7. What about our y1? Our y1, our x naught is above, is 2. Put it in this equation. Where there is y, put the value of x naught, which is 2 square plus 3, square the result, then add 3 to the result. Remember, you're doing it mod 2029. You're doing it mod 2029. Was it 2029 or 2929? I think it was 2929. Yeah, it is here, in fact. Now, so 2 square is 4, plus 3 is 7. When you square this 7, is 49. 49 plus 3 is 52. That's our x, yk, y1. Subtract x1 from y1. You get 45. And find this GCD. This GCD is 1. When you find it's 1, it means you proceed the next step. Find x2. Find x2. How do you find x2? x2 will be, our x just above is 7. Put it in this equation. Put it in this equation. Substitute it there. 7, substitute there. You have 7 square plus 3 is 49, 52. 52. Let's find y2. What is y1? Y1 is 52. Substitute 52 in this equation of yk. So what that means is 52 square plus 3. Square that result. Then add 3 to the result. Do this mod 2929. Our calculator. calculator here. Okay, 52 square is 2707. 2707 is less than this. So I can proceed, I can add 3 to it. I can add 3 to it and get 2707. What was the other one? Just a minute. 52 square, what was it? 52 square was 2704. 2704, which is smaller than this, our divisor. Since it is smaller than this divisor, let me proceed and add 3 to it and get 2707. 2707 is still smaller than this. Otherwise, I would have reduced it. Otherwise, I would have reduced it mod 2929 so that my calculator can accommodate it. I reduce it. I want to deal with smaller numbers. So I have 2707, which is small. So let me now square that result actually. Square it. When you square it, you have 7,327,849. You can add 3 to it. And add 3. Divide this result by 2929, which goes there. How many times? 2501 times. 2501 times. What is the remainder? 2501 times. The remainder is 2423. 2423 is the remainder. At this point, subtract 2423 minus 52. You get 2771. Find this just using Euclid's algorithm. Find that. And of course, that one you're also doing it because you already have, you will then be having also a program for that. Euclid's algorithm for doing the GCD. And you get 1. Once you get 1, it means proceed and find X3 and Y3. So let's proceed and get X3 and Y3. Until we get a value that is not 1 and is between, remember the value that we need to get to stop should be a value greater than 1 and less than n. If we find that the value we get is n, it means we begin afresh. Begin afresh by setting our initial conditions properly. It's because the program will have failed. So we found our GCD to be 1. That means we still have some work to do. Let's now find X3. What is X2? X2 is 52. Substitute it in this equation of XK. Substitute that equation, 52 in that equation, the 52 square plus 3. We're doing this mod 2929. My calculator, what is 52 square? Okay, 52 square is 2704. Then add 3 to it. Get 2707, which is smaller than this, 2707. Let's get Y3. I'm sure at this point, we now know what is happening here. To get X3, we're using Y3, we're using Y just above, which is Y2. That y2 substitute in this equation of yk. Y2 is this. So that means we are squaring 24, 23, then adding 3 to the result, then is squaring the new result, and adding 3 to it, then reduce mod 29, 29. Our calculator comes in 24, 23 squared. It's 5,870,929. This is a very big number. Let's reduce it first before adding 3 to it. Or alternatively, we can add 3 to it. Yes, let's just add 3. Let's just finish with this bracket. Let's just add 3 to it. So when I add 3 to it, what I get inside this bracket is 5,870,932. This is the number I want to square, then add 3 to it. But I've noted that if I square it the way it is, it will give me a very huge number. So let me reduce it first using this mod. I reduce it first using that mod. Let's reduce it. Mod 29, 29, which goes there 2,004 times. 2,004 times. 2,004 times. The remainder is small the way you want. So this is the one I can now square and add 3 to it. Then again reduce by the mod. So what happens when I square it? When I square it, I get 1,478,656. Let me add 3 to it. What have I gotten? I've gotten 1,478,659. So let me reduce it mod 29, 29, which goes there 504 times, 504, 504, 504. The remainder is 2443. That's our remainder. These are y3, subtract what x3 from it. Subtract x3. X3 is 2707. And take the absolute value. Take absolute. Your result, you take positive, you ignore the negative. So what I have is 264. Find this GCD. I found it to be 1 using the Euclidean algorithm. That means, again, we have to proceed and find x4 and y4. You have to get x4 and y4. Good. At this point, we are now together. We know that to get x4, we're using x3, and we are substituting the value of x3 in the equation of xk, which is here, equation of xk. And our x3 is 2707. We are squaring it, adding 3 to the result, then reducing mod 29, 29. Again, when you do this, you'll get 24, 23. And let's get y4. Y4, you're using y3. Substituting the value of y3 in the equation of yk, which is here. So what is it? Y3 is 2443. 2443. Square it, then add 3 to the result. Square the new result, and then add 3 to the result. Then reduce mod 29, 29. You can see how big this value is. Square it, add 3, then reduce it. Let me just do this part of Y4. Just do that part. We first of all work out the bracket before squaring. Because when you square it, it will be a very huge number. So 2443. Square that, you get 5,968,249. Add 3 to that result. Let's reduce it. Mod 2929. Divide by 2929. Divided by 2929. And it goes there 2037. 2037. 2037. The remainder is what is important here. 1879. Let's now square it and add 3 to it. Then the new result, we shall reduce it. Mod 2929 again, because it will be bigger than that. Once it becomes bigger than 2929, you reduce it. Okay, so 1879. Square that. You have 3,530,641. Add 3 to it. That result, divide by 2929. It goes there 1205 times. 1205. 1205. 1205. The remainder is 1199. Now, get the difference between these two. You can even subtract this from that, or subtract this from that, and ignore the negative, whichever you want. The result is the same. So let me subtract 2423 minus 1199. I get 1224. Then do this GCD using the Euclidean algorithm, and you get 1. It means you proceed and find x5, y5. Find x5, 5. You proceed that way, it will give you a factor. It will give you a factor. Whoever came up with this method, it's a genius. It will give you a factor. And that guy is called now, so x5. What is x4? 3. And reduce the result mod 2929, since it will be bigger than that. This is one, when doing that, you get 16. What is our? So it will be square plus square mod 29. Again, the number Okay. I'm sure you've not lost me for long. Have you lost me for long?
No, just a minute. We are good.
It's okay. Now, so the number inside the bracket is again big, so we work that one out first. Let's do that. Is a calculator. You have 1199. Square that number. You have 1,437,601. Divide, add 3 to it. Add 3 to it. Good. Divide. We want to reduce it first of all before squaring. Want to reduce it because whatever is inside the bracket that I'm seeing here is 1437, 604. This is what we want to square. Then add 3 to it, mod 2929. But this number is very huge. Calculator may have failed to accommodate the square. Let's just reduce our square first of all. Divided by 2929. It goes there 490 times. 490. What is the remainder? The remainder, 490 times. The remainder is 23. $94. This is now the number to it, and then reduce 29. Let us square it. We have 5,731,236. Add 3 to it. Then divide by 29, which goes there 1956 times. 1956 times. The remainder is 2115. 2115. 2115 minus 1216 gives us 899. This GCD gives us 20. This is the first time we've gotten a value that is not 1. Therefore, this value is a factor of the factor of n. 29, therefore, is a factor of n. If you want to get the other factor, you divide 29 by 29. So, but what we're interested in is the value there. So, if the 29 was our n, then we can say that maybe our p is 29, and maybe our q is another value that we just divide 29 by 29 and get it to be 101. And so, if this was the RSN, then we have the values that were used to find n, and then we can find our q, our phi of n. And once we find phi of n, and we know that E was public, is a public key, you can get, and you know that you get D is E inverse mod phi of n. So you have D. Once you have D, and you know that the ciphertext, you have it, you can take that ciphertext and then decrypt it to get the plain text. That's what we'll be doing. That's what we'll be doing when we meet. Good. There are several other examples. If in case this We have it was not clear. Again, we shall look at several examples. We have several examples, so we look at them maybe next time. But that is just the same way we are doing. There's not, that's the way we do it. You can only vary, if you want, you can just vary the 3 with the, but at your own time, try another value. You can try 1 and do it. You see, the number of steps you take may vary. The number of steps you take may vary. For instance, here I had 5 steps, and when you change your 3 to be 1, and maybe you may have more steps or maybe less steps. So it depends. You can even change this to 7, but use the same logic, the same reasoning. So the only difference would be that the number of steps will be more or less compared to mine. So, but any number there would work. Any question here would work. Thank you.
All right. Thank you, Dr. Sakwa, for that class. I will see you guys on Thursday. Have a good evening.